So in the previous module, I talked about the calculations of Laguerre polynomial and associated Laguerre polynomial, and I gave you a table in which all the terms of Laguerre polynomial and associated Laguerre polynomial was tabulated for different values of n and l, and I said you it's for 1s, it was for 1s, 2s, 2p, 3s, 3p, 3d, and 4s also. But 4p, 4d, 4f, I have not given you, and I said you that you will be doing, and you can find out for 4p, 4d, and 4f different values of Laguerre polynomial and associated Laguerre polynomial. That was your homework. Okay. I hope you have done it, and once you have done it, you can come to this module, and you see now we are going to calculate the radial wave function for different orbitals of hydrogen atom. So for n is equal to 1 and L is equal to 0, that's 1s orbital, I said you in the previous case. The basic equations for R and L R is given on the top of this slide, that the first function under the square root is the normalization factor, and then exponential minus rho divided by 2, we got the asymptotic solution, so it is there. And you should remember that rho is equal to 2zr divided by Na0, where A0 is the Bohr's radius, n is the principal quantum number, and z is the atomic number. Okay, and then we have associated Laguerre polynomial as 2ln plus l, 2l plus 1. So for in this case, for 1s orbital, the associated Laguerre polynomial which we are going to use is L11 rho, and that is equal to 1. Okay, that we know that's equal to 1, or you can see from the table this is equal to 1. Okay, from the previous table it is given. So now we have L11 rho is equal to 1, and rest of the thing is simply calculating the normalization constant. So it is 2z n is equal to 1, 2z divided by A0, 1 minus 0 minus 1 factorial, 2 into 1, and 1 plus 0 is equal to 2, and 1 plus 0 factorial raised to the power 3. So it comes out to be, your R10 comes out to be 2z divided by A0 to the power 3 by 2 exponential minus rho divided by 2. Okay. So what does it mean? It means it is 2 z is equal to 1 A0 exponential minus rho, and rho is what? Rho is 2 zr divided by Na0, n is equal to 1. So A0, okay, into 2. 2 is there because the rho divided by 2 is there, so into 2. So what does it make? It makes 2 into 1 by A0 exponential minus 2, and 2 will go, z will become 1 minus r divided by A0. Okay. So your final equation is 2, okay, it is already given here, 2 1 over A0 raised to the power 3 by 2 exponential minus r divided by A0. Okay. So A0 is a constant. So you have, in every case, you will find that you have some constant. This is a constant. And then how does the function depends upon the r is given here. Okay. So r divided 1 over A0 will also be a constant. So the only function which tells you is minus r, exponential minus r. Okay. So R10, r is proportional to exponential minus r. Okay. What does it mean? It means r is the distance away from the nucleus. So if you move away from the nucleus, the function goes on decreasing exponentially. That's very important. For 1s orbital, the wave function which we have obtained, it goes on decreasing exponentially as you go away from the nucleus. So these calculations are important because that tells you that what is the fate of the radial part of the wave function if you move away from the nucleus and r goes on increasing. Okay. For 1s orbital, we have seen that it's proportional to exponential minus r. Okay. Some constant is there, but we can neglect that constant. The constant will not tell you the dependence of the wave function. Okay. If you go for another function, for 2s orbital, then again the associated Laguerre polynomial which you have to use is L21 rho, and L21 rho we have already determined as 2 into 2 minus rho. Okay, and if you find out this part, normalization constant part, then 2z divided by 2 is 0, so z divided by 0 to the power 3, and then 2 minus 0 minus 1, so it's factorial 1, so it will be 1, and 2 into 2 will be 4, and here you have 2, so 4 into 2 will be 8. Okay, so factorial of this will be raised to the power 3. It is 2 minus 0, so raised to the power 3 is 8, and 4 here, so 8 multiplied by 4 is will be there, and exponential minus rho divided by 2, 2 into 2 minus rho. Okay, so what happens if you finally what you get is z divided by a naught, R20 is actually 1 over 2 root 2, z divided by a naught to the power 3 by 2, exponential minus rho by 2, 2 minus rho, and 1 by, or look at this one here, this part 1 over 2 root 2, 1 over a naught raised to the power 3 by 2 is a constant. This is a constant. Understand it in the sorry, it's a constant. Okay, so what you have is exponential minus r divided by 2a naught and 2 minus r divided by a naught is the function. So you have one function which is exponentially decreasing r, and another is factor is 2 minus r divided by a naught. Okay, what does this function tells you physically? Suppose r is equal to 2a naught. At this point r is equal to 2a naught. If you put this value here, what will happen? It will be 2 minus 2a naught divided by a naught within bracket, so it will become 0, and the whole function will become 0. Okay, so at r is equal to 2a naught, the function r20 r becomes equal to 0, and if the function becomes equal to 0, the square of the function will also be 0, and the probability will be 0, and that will be the nodal point. So 2s orbital has a node, the radial node. 2s orbital has a radial node. The concept of radial node comes from this equation. Okay, then at r is equal to 2a naught, if you put r is equal to 2a naught, then this function will also be 0. Okay, because the whole function has to be 0, and if r is greater than 2a naught, okay, then again the function will start decreasing. We will come to the plot also later on. Okay, so at least the existence of one radial node in 2s orbital is very obvious from this equation, and that you know that 2s orbital has a node, but now we have a mathematical explanation for the existence of one radial node in 2s orbital. Okay, what about 2p orbital? If you look at 2p orbital, the associated Lagrange polynomial which you require is L33 rho, and this we have already determined and it is tabulated already. It's the value of this is equal to 6. Okay, and if it is 6, then the final value R21, which is the same normalization constant process which we did earlier, if you finally find out, the value comes out to be 1 over 2 root 6, 1 over a naught, 5 divided by 2, r into exponential minus r divided by 2 a naught. Okay, so you have two different factors. Again this part is a constant, this part is a constant. Remember, a naught is Bohr's radius, which has a constant value 0.529 angstrom. So this part is a constant. You have two factors, one is pre-exponential factor and another is exponential factor. Okay, so these two will influence with increasing r value, the pre-exponential factor will try to increase the function, and the exponential factor will try to decrease the function, and we will see the effect of these two factors on the functions when we plot this curve. Okay, 2p orbital. For 3s orbital, if you look, Then 3s orbital, you require associated Lagrange polynomial is L3 1 row, and this we know L3 1 row is 3 into within bracket 6 minus 6 row plus row square. Okay. So if you use this associated Lagrange polynomial L3 1 row and you find out the values, then finally then you have the value. The final value is this one, 2 divided by 81 root 3 z divided by a naught to the power 3 by 2. Then you have 27 minus 18 zr divided by a naught plus 2 zr divided by a naught square exponential minus zr divided by 3 a naught. Okay. So if you look at this one, this part, you do not have any r. You do not have any r. So this is a constant value. Same way, here also, this part is a constant. Okay. So we can say it's a normalization constant sort of thing. Okay. If you look at in terms of rho, it looks easier to see the rho equation because it is 2 zeta divided by n naught written in the form. If you look at this equation, again you have a exponential equation, exponential minus rho divided by 2, and then another equation which is pre-exponential part, which I have written as post-exponential, but you can write pre-exponential also, which is 6 minus 6 rho plus rho square. So this equation 6 minus 6 rho square is a quadratic equation. Here also you see zeta divided by a naught square, then you have zeta divided by a naught, then a constant value 27. So what does it mean? For two different values of r, this quadratic equation, since it is a quadratic equation, so for two different values of r, this quadratic equation will be 0. Okay. So the function will be 0, r3 naught will be 0 for two different values of r. And so it tells you the existence of two radial nodes in 3s orbitals. Okay. So this is very important. So now you are able to see that why we have done all those calculations, radial functions, finding out the radial function, finding out the Lagrange polynomial, then finding out the associated Lagrange polynomial. Our goal is to get the value of radial part of the wave functions for different orbitals, for different values of n and l. Orbitals we will not say, for different values of n and l. And that will give you an idea about the physical picture of the electron within the hydrogen atom. And that physical picture these are the results which we are already known to you, but the mathematical explanation to these results you were not knowing. You were not knowing that why it is, if n is equal to 2, L have only two values, 0 and 1. I showed you how why the L value is restricted, why it is not 0, 1, 2 for n is equal to 2. So, and you were knowing that 1s orbital has no node, but 2s orbital has one node, 3s orbital has two node. So you see, for two different existence of two radial nodes we see in the formula, because it's a quadratic equation, and so for two different values of r, this equation will be 0. Okay. So this way we are able to explain the things which were known to you qualitatively. Now we can talk about in quantitative terms through the radial wave functions. Okay, through mathematical equations we can talk about. Okay, for 3s orbital. For 3p orbitals, if you see 3p orbitals, then it is the associated Lagrange polynomial which you require is L4 3p rho, and this is actually 24 multiplied by 4 minus rho. Okay. And if you bring 24 this side as a constant, then finally what you get? Again you get a constant value, multiplied by exponential minus rho divided by 2, rho 4 minus rho. Okay. So again, if you look at this one, 4 minus rho, what you can write? 4 is equal to minus 2 ZR divided by NA naught. So you can write 4 minus 2, Z is equal to 1. So R, N is equal to how much? 3 A naught. Okay. So what you can say, if R is equal to 1.5 A naught, okay, not 1.5, how much it should be? It has to come 12. So it should be how much? If you put 2R divided by 3A naught is equal to 4, then what do you get? You get 2R is equal to 12A naught, or R is equal to 6A naught. Okay. So if you put R is equal to 6A naught, what do you get? 4, 6A naught divided by 3A naught. So this 12 divided by 3 is 4, and you get 0. So the moment R is equal to 6A naught, the function will be 0 for the 3p, and you will have a node there. Okay. This is how you interpret radial wave functions. Radial wave functions are interpreted as how does the function depends if you go away from the nucleus for each of these combination of principal quantum number and azimuthal quantum number. Okay. So we saw the different dependence in case of 1s, in case of 2s, in case of 2p, in case of 3s, in case of 3p. So, and same you can do for 3D also, and we can calculate this one. Okay. So for 3D again you have a constant. The value you see, all these values which is tabulated in the previous module, we are using L55 rho. I think it is tabulated in the previous module, and which was 120. This was the last, I think, in the table. So the value was 120. So we get the final equation as a constant multiplied by exponential minus exponential minus rho divided by 2 into rho square. Okay. So a pre-exponential factor and a exponential factor we have here. Similar way one can go and find out the 3f orbitals also. 4s orbital now. You see there are 4s orbital also, and L41 also I determined. So it is also in the table. 4s orbital again you see it is 24 minus 3s rho plus 12 rho square and rho cube. Obviously, in this case, since it is rho cube, so there will be 3 different values of R for which this equation will be 0. I think 3 different values of R for which it will be 0, and will make the whole function, or better write R40 R function 0. Okay. What does it mean? It means we have 3 different nodes for a 4s orbital. Look, 1s orbital, no node was there. 2s orbital, 1 node was there. 3s orbital, 2 nodes were there, and 4s orbital, 3 nodes are there. Okay. And it's very obvious from the equation, because in case of 2s orbital you have 2 minus rho. In case of 3s orbital you have a quadratic equation. In case of 4s orbital you have a equation rho raised to the power 3. So you have 3 different values for this equation at which the function will be 0. So we are trying to explain all those observations, all those informations which we are already having through quantum mechanical calculations, through the calculations of radial wave functions. So these mathematics is very important. I said in the very beginning that the language of quantum mechanics is mathematics. One cannot skip mathematics and do the quantum mechanics. If you don't do the mathematics, you cannot do the quantum mechanics. But this module especially and this course especially I have designed, and the slides I have designed in such a way that any one of you who is little aware of the differentiation and integration, and which is very basics of the mathematics, can do it on your own. The only thing which will be required will be a practice. So these videos are not for the purpose of just watching it. These videos are serious videos where you have to sit together along with a pen and paper and do all these calculations on your own, and you will be able to get these results on your own once if you go through it very seriously with a pen and paper. If you just watch it, then it will not be a very useful video. On all these interpretations, if you want to see, you will get in any quantum chemistry book, you will get a table which will give you Laguerre polynomial and associated Laguerre polynomial, and then it will give you the value of R10 and R20 and R30 and 40 and all those things. The explanations, if you want to see, and if you want to see the very basics of these, then you can go for, I would refer you to go and look at the book of University Chemistry by B.H. Mahan. University Chemistry. Before you go for any quantum chemistry book, you at least read this one. This is a very basic book, University Chemistry by B.H. Mahan, Bruce H. Mahan. At least the chapter of atomic structure you should read it from here, and then you go for a quantum chemistry book. Okay, that will be very helpful for you in understanding the things. And these stepwise calculations, if you need in a book, then the Quantum Mechanics by Pauling and Wilson is a good book where many steps is given, but not all these steps are given. In any book you will not find all these steps which is done here on these slides. But Pauling and Wilson will be a good book to follow if you want to do the mathematical calculations of these. Okay, but you don't need it. You just go through the slides and write the equations, do the calculations on your own, and you will understand it's very easy to do all these calculations. Okay, so these are the different radial wave functions which I have calculated, and I have given you the importance of these radial wave functions, that how these radial wave functions tell you the dependence of radial part of the wave functions on the radius, on the r function, because we have started talking about hydrogen atom by using the spherical polar coordinates, and in spherical polar coordinates we have three different equations, three different variables, r, theta and phi. So this was the part of the wave functions, radial part of the wave functions and radial dependence of the wave functions we talked about. We do have the solutions for angular part of the wave functions also. Angular part of the wave functions gives you angular dependence of the equation of the wave functions of hydrogen atom. And I said you that angular part is a combination of two different functions, phi functions and theta functions. So we combine them together to get you to give a new function, and that new function is called spherical harmonics. And if you go for the previous slides, you will find that there is a one table in which all the spherical harmonics is written. Spherical harmonics is shown as YLM, where L is azimuthal quantum number and M is magnetic quantum number. So for different values of 0, 0, 0, 1, 0, and where you see 0, 0, what does it mean? L is equal to 0, azimuthal quantum number is 0, magnetic quantum number is 0. What does it mean? It means we are talking about s orbital. Which s orbital we don't know, because n is not given. If n is equal to 1, then it is 1s. If n is equal to 2, then it is 2s. If n is equal to 3, then it is 3s, and so on. Okay. So we are talking about here only s orbital. We cannot say which s orbital, but s orbital has this you see spherical harmonics of angular dependence of wave function and angular dependence of wave function. So y00 is 1 over root under 4 pi is for the s orbital. Now y is equal to 1, 0. So 1, 0 is L is equal to 1, m is equal to 0. So L is equal to 1 means it's a p orbital. Which p orbital? I will not write. We will see which p orbital it is this. Then y1 plus 1 and y1 minus 1. This is also p orbital. Which p orbital? We don't know. But the problem with this is the function exponential I phi and exponential minus I phi. And I said you earlier that whenever you have a function which is imaginary, you have to convert this imaginary function into real functions. Okay. If L is equal to 2, what is this? 2 means it is, see, 0, 1, 2, 3. If L is equal to this one, 0 refers to s orbital, 1 refers to p orbital, 2 refers to d orbital, 3 refers to f orbital. So all this in this table on the right hand side in this column, it's all L is equal to 2, so it's all d orbitals. And how many of this you have? 1, 2, 3, 4, 5 of this you have. And you know d has 5 different orbitals. How many of p you have? 1, 2, 3 you have. So p has three orbitals, and that you are aware of. That if you use a box of d orbitals, you write 5 different d orbitals. If you draw a box of p orbitals, then you draw 3 different p orbitals. Okay, and if you write s orbital, you draw only one box. Okay, but the issue is here of the imaginary functions. And if I remember, I talked about that we can convert this imaginary function into real functions. And for that, what we do, we take for the time being, I am talking about p orbital only. We take a linear combination of these two orbitals, plus 1 and minus 1, and then multiply it by 1 by root 2 or minus I by root 2, okay, which was the constant. I will not go to the previous slide. You can go and see with the calculation I have given you. Okay, so if you do that, it's not there. y3 plus 1 is not there. See how many of this is there? 1, 2, 3, 4, 5, 6, 7 is there. So you can copy it from any book or you can calculate yourself these spherical harmonics. So if you look at these spherical harmonics, and if you look at the s orbital, what is this? It is y0, 0 is 1 over root under 4 pi. And what does it mean? There is no theta and there is no phi in the function. And if you remember correctly, if I draw a coordinate system, okay, x, y and z, and if this was your r, your particle is here, then what do you say? You draw a perpendicular from this in the xy plane and then join this point with the origin, and the angle which it is making is phi angle, and the angle this r is making here with the z is theta angle. Now I say that in case of y0, 0, you do not have theta and phi. It means, what does it mean? All values of theta is equally probable. Okay, it could be anything. So the function could be anywhere, right from plus z to minus z in this direction, or in this direction. It is possible. Okay, so it doesn't depend upon theta and phi, and that is why s orbital is spherical. For any s orbital, L has to be equal to 0, M has to be equal to 0, whether it's 1s, 2s, 3s, 4s. Okay. So angular dependence tells you that s orbital is spherical because the spherical harmonics does not contain theta and phi. Now, if you go back to the radial part tells you that for 1s orbital, the function is decreasing. For 2s orbital, you have a radial node. For 3s orbital, you have a two radial nodes. For 4s orbitals, you have 3 radial nodes. Okay. So what does it mean? If you want to draw the picture, then you will draw a small sphere originating from with the origin at the center for the 1s orbital. Then there will be a space where that will be radial space, because for 2s orbital you have a radial node, and then again there will be a probability around this one. Okay, and this density will go on decreasing as you go away from the nucleus because of the exponential function. Exponential function is exponential minus r divided by something. So as the r value increases, the exponential function will decrease. So if you try to interpret these results for 1s orbital, it's like this one. Okay. So for 1s orbital, n is equal to 1, L is equal to 0, and m is equal to 0. So the spherical harmonics is y0, 0, and y0 is 1 divided by root under 4 pi. The spherical harmonics is independent of theta and phi, and therefore s orbital wave function is said to be spherically symmetrical. So now you have an answer that why it is so that all s orbitals are spherical in shape. Okay, and you see the from the origin, this is your r distance. Okay, from the origin, this is your r distance. As the r increases, the electron density will go on decreasing. Okay, or the function also will go on decreasing as you go away from the center, from the origin. So for s orbital, we talked about the radial dependence of the function and the angular dependence of the function. Both. S orbital is spherical, but if you go from 1s to 2s, 2s to 3s, 3s to 4s, in each step you are increasing one node. 2s will have one node, 3s will have two nodes, 4s will have three nodes. That the concept of nodes comes from the radial part of the wave functions. The concept of the shape of the orbital comes from theta and phi equation, that is spherical harmonics. Okay, we will continue talking about other functions, p functions and d functions in the next class. P functions and further radial distribution functions and all the details in the next module. Thank you.